So let's see how IMT is really just Newton's second law. And we'll just look at maybe just one of them, and you can see the difference between the two. So let's say we're looking at the net torque, okay? Well, according to this up here, that's going to be the change in angular momentum. This is always the net torque here, by the way. Net, and that's the net force, net, we're always talking about the net, okay, over dt. And to find the angular momentum, well, that would be the rotational inertia times the angular speed, but it's changing. So the rotational inertia is usually the thing that doesn't change. So it's I change in omega like that, and we leave change in t right here. And then hopefully this right here might look a little bit familiar. That is alpha. That's the angular acceleration. So this is really just I alpha, and lo and behold, the net torque then is equal to I alpha, which is Newton's second law in rotational form. So that's really all the impulse momentum theorem is. Okay, so you might see problems where you are given some little piece of information, one piece, two piece, three piece, and you have to use some form of the equation, some form. Maybe you have a graph, maybe you'll have just enough, right? And you have to figure out what's going to happen next. But conceptually, if you apply a torque for a longer amount of time, you'll get a greater change in angular momentum. And if you change your torque, okay, then you'll have a different angular momentum. So, and if you need to change the angular momentum a different amount, then you can change your torque or your time, just like we could do with the angular impulse, okay, or the linear impulse. Make sure you ask questions if you have them. Thanks for watching. Hi guys, this is Mrs. Gastler, and in this video we're going to talk about angular impulse. And so we're going to talk about having this object here that has some angular, rotational momentum. It has a radius r, and maybe we'll talk about this point here individually or as a part of the whole. All of these little pieces in here, this object is made up of a bunch of little pieces that all are moving together. It is called a rigid body. Okay, it's just a solid object. Okay, that's code for a solid object where all the pieces rotate together. Okay, it's not like Jello or soup or something where you turn it and it doesn't all go together, but the whole thing rotates together like this pencil. Whee! Okay, and we're going to apply a force on it. Okay, in this direction, and so that's going to mean that we're applying a torque, which is R F sine of phi, and just to remind you that phi is measured right here. Okay, phi. Theta would be the displacement that would experience, which would be measured over here after I've moved it. I haven't moved it yet, but that's where theta would be, okay? And in AP Physics C, that would be R cross F, like that, okay? Depending on where those things are, okay? Now, when we talk about linear impulse, okay, that was Jimpulse, okay, which if you don't have to call it that, but you can if you want to. J, that's a J, maybe like the bar on top and a little loop that goes up, however you like to write your J's. J is for impulse. Linear impulse is F times the change in time. So impulse happens when you apply a force for an amount of time, and that's how you find it there. And for the calculus version mechanics, we find that by doing the integral of f dt, because sometimes the f isn't constant and it changes over time. And what this means in AP Physics 1 is that if you have a graph, you would just find the area under the curve. Maybe you can do that by geometry, and maybe you're just looking at it, okay? Either way is fine. And if we look at the angular impulse, which I really don't want to write again, so I'm just going to abbreviate that, ang-imp. Okay, and you can write that out if you'd like to. Instead, angular impulse. Maybe I don't want to call it AI. That stands for something else right now. So the angular impulse, it doesn't actually have its own, letter or abbreviation. In fact, we don't usually write it down. We write it some other way. But so let's do our equivalent thing. So instead of force, when we talk about angular stuff, we use torque. But the time stays the same, so it's delta t. Okay, And so if we were in mechanics, we would write the same thing. Oh gosh, angular impulse. But this time we'd do the integral of torque dt. Okay. I know it's got lots of different t's there, so make sure your t's and your torques, your taus look different. Okay. Now, what we usually write when we talk about angular impulse, and often when we talk about linear impulse, is the impulse momentum theorem. Impulse momentum theorem. And oh my gosh, I don't really want to write that out again either, so I'm going to write IMT, okay? The impulse momentum theorem, okay, in linear form, and continuing on down over here, is F delta T, that impulse is equal to the change in momentum, okay? And sometimes we write that in terms of the force, like this, delta P over delta T. And sometimes we don't. Usually we just write it like that. So this right here, let me put a pencil box around it. That's the impulse momentum theorem right there. Okay, but often this is a useful way to write it and think about it. Okay, and if we were in mechanics, what do you call it? Calculus version, we might write it like this, which is dp. And then we might have to do some fun calculus in there, but that's what it looks like. And then writing this is actually really useful in AP Physics C because it's the derivative. Ooh. But this right here is the impulse momentum theorem. Okay. Ooh. Hold up, I dropped my pen. And knocked into the camera. Okay. All right, so the angular version of the impulse momentum theorem looks pretty much the same. Okay, so instead of F, we have torque. Instead of delta, oh no, delta T stays the same, okay? And instead of delta P, we're gonna have some music in the background. And instead of delta T, we have delta P, we have delta L, okay? And then instead of writing it F, we'd write torque equals delta L over delta T, okay? But this right here, this is what we usually write even instead of this up here, because we don't have a formula or a letter for angular impulse. Now, the CM version is going to be torque dt equals dl, and then when we write that, we get that derivative again, torque equals dl dt, okay? But again, this right there, that's the impulse momentum theorem. Now, impulse momentum theorem, MT, is really just Newton's second law. So Newton's bell's going to ring, and they're probably going to make some announcements.